we're ready to talk about cycloalkanes, looking at section 5 from our chapter on alkane chemistry. It says that a hydrocarbon that contains carbon atoms joined to form a ring are known as cyclic hydrocarbons. When all those carbons in the ring are saturated, just single-to-single bonds, we call that a cycloalkane. We see in nature a range of cycloalkanes from being a simple 3-ring, which would look like a triangle, all the way to more complicated, much larger rings, 30 carbon atoms or more. And truly, there would be theoretically an infinite number of carbons you can link into a cyclic structure. Cyclopropane, cyclobutane, cyclopentane, cyclohexane, and so forth, joining the carbons end to end from a long carbon chain. Thinking about our last straight chain rule, where we learned 2n plus 2 gives us the formula where n represents the number of carbons. When we hook together the chain, and let me just cut a model. If I hook together propane, which is a straight chain molecule, and take these 2 carbons here at the end, here and here, and actually bring them together and attach into this cyclic structure, you can see to hook them together we have to eliminate a hydrogen off of each end. So the cycloalkanes is simply a formula of 2n. We eliminate the plus 2, so we have to remove those hydrogens there at the end, those terminal carbons, to create bonding spots to actually hook those carbons together in the cyclic structure. So again, here's cyclobutane, 4 carbons. There would be 1, 2, 3, 4, 5, 6, 7, 8 hydrogens. 2n gives us the cyclo structure. Cyclopentane, C5H10. Cyclohexane, C6H12. All a saturated molecule, meaning that they're all single-to-single bonds. So we hear this name of cyclo hooked to this last chain here of the alkane, where the prefix of the corresponding open chain, so the same number of carbon atoms, that determines the last name, but it gets this little prefix cyclo, indicating that the terminal carbons have now linked together. Just as before, we name the substituent groups on the ring, kind of prioritizing by alphabet. Interesting, if there's only one substituent group on a cyclic structure, we automatically know that it's assumed to be at the position of carbon 1, so there is no need to give it a location number. It would be redundant. Priority is given to the substituent carbon right here. This looks like 1, 2, 3 carbons coming off of the carbon number 1 in the chain. Looking at that branched group of 3 carbons, isopropyl cyclopentane. Right here is the structural group here, the isopropyl alkyl group. Prefix cyclo lets us know that the 5 carbons are indeed in a ring. And just if you were to build this molecule with your molecular models, it honestly would not matter where I placed those, where the isopropyl group comes off, because it would always get the same priority as being carbon 1. Here's a molecule. I see a cyclic structure, so that will automatically become the root word. I have 1, 2, 3, 4, 5, 6. So my ending here is cyclohexane. I have 2 substituent groups, 2 branches coming off. So now I'm going to number those in order of alphabetical order. So here, again, we have a tertiary butyl. I have carbon 1, 2, 3, 4. The carbon that's coming off the branch here has 3 carbons attached to it. That's where the tert comes from. So tertiary means that the carbon attached to the ring is branched with 3 carbons on it. We had discussed that in an earlier lesson. So tert does not become part of the alphabetizing priority, just like primary, secondary, tertiary. So carbon number 1 is being called priority because of the B from butyl. 1, tertiary, butyl, and on the other side we have 1 carbon, 4, methyl cyclohexane. Notice the numbers get a dash to the prefixes, 1 dash tertiary dash butyl dash 4, and then when I finally hook it to the root word, it goes right in order. If we had more than one group coming off, remember that we would use commas between the numbers. Oh, let's just suppose I had another methyl group coming off at carbon 1, 2, 3. If I had another methyl group coming off, it would still be 1 tertiary butyl. That's what this whole compound here is, this little group, tertiary butyl compound, a little branch. But now I'd have 3, 4 dimethyl cyclohexane. So commas if we have more than one in a row there. Alrighty. So let's just take a quick practice and try some more examples of naming cyclic structures. And I'm just going to pull from the bottom of page 333. The first structure I see in letter A, I have looks to me like a house, but it's a 5-member ring. And I have 1, 2, and then a branch. Alrighty, so let's name this following structure. Well, right here I know that this is going to become carbon 1, 2, 3, 4, 5. There are 5 carbons in this cyclic structure, so I know cyclopentane will be the ending. Carbon 1 gets a priority at this point because that's where the branch is coming off, the alkyl group. How many carbons do we count in the alkyl group? Well, I have 1, 2, then I notice a branch, and that's the iso branch, isn't it? 3, 4. This is isobutyl functional group. Isobutyl, and that should be attached to cyclopentane. So I'm going to just kind of grab that and move it over, and now we have an imagination going. Isobutyl cyclopentane, all one word. Isobutyl cyclopentane. Now just to remind ourselves, the last time we had seen a branch, a little bit different, and I'll just make one up here, it looked a lot like this. Well, when I count that structure, again, it's cyclopentane, but now this alkyl group, it has a total of 1, 2, 3, 4 carbons in it. Those 4 carbons are also butyl, but notice here the iso part of it, the iso means a branch at the terminal end. It's a little different because this guy, this carbon in the center, has 3 carbons around it. There's where you see that prefix tert. Tert butyl stands for tertiary. Tertiary butyl is that functional group. Let's try another. I'm counting in the second structure, the letter B, how many sides we have, and I'm just going to count 1, 2, 3, 4, 5, 6, 7. I'm going to try to draw a 7-sided ring. 1, 2, 3, 4, 5, 6, 7. Oh, that's not too bad. And then coming off of it, I have the following functional group. Alrighty. Name that structure, and boy, that looks fun. So I'm going to try to count how many we have. And again, this would get top priority, so there's carbon 1, 2, 3, 4, 5, 6, 7. I tried to draw a 7-sided ring. So now I know cycloheptane is my ending. Now I'm seeing an alkyl group coming off. It's not iso, it's not a branch where it's terminal with 2 carbons hanging off. So in this branch I have 1, 2, 3 carbons coming off, propyl, and at carbon number 1 there's a methyl group. So right here is an additional carbon. So putting this together, we have 1 methyl. 1 methyl is saying attached to this. Propyl, cycloheptane. 1 methyl propyl cycloheptane. And there should be a dash right there. 1 methyl propyl cyclohexane. Heptane, I'm saying the wrong word, heptane. 7 carbon ring. Propyl cycloheptane, all as one attached word. And that'll just take some practice for you. Count. knowing that the end comes from the root word, 7 carbons heptane, and just start naming the branches as we did the straight chains. The conformations of alkanes discuss the shapes of the alkanes along with the cycloalkane. So this little section is going to refer to the conformation of three-dimensional, geometric shapes that these molecules will take in space. And again, if you have yet to get yourself a kit of molecular models, it really pays dividends in this class. A ball and stick model where we can create these shapes and study them. And it says the Vesper model gives us a way to predict the geometry about each carbon in an alkane, but it really provides us no information about the 3D shape of the entire molecule. So Vesper theory says about a specific atom, like I can talk a Vesper around this atom or this particular atom, but it really is limiting in terms of an entire molecule. So when we talk about conformations, we're looking at the entire structure of the molecule in terms of how it arranges all of the atoms in space. Those are what's known as conformations. So the molecule, as simple as ethane, could have an infinite number of the way that the bond rotates itself around its axes of carbon-to-carbon bond. If we think about conformations of butane, and again, here's a straight chain carbon, C4, H, okay, so 2N plus 2 gives us 10 carbons. This is butane, a straight chain. If you were to connect 4 carbons using your molecular model and place on the hydrogens and just start rotating those bonds, because they're not rigid, but they have the freedom to move around in a three-dimensional way. What are all the different possible conformations, all the different bond angles just by rotating the way the carbon-to-carbons are connected? That's what we mean by a conformation. Here's 3 possible conformations. Although there's an infinite number, just by moving 1 degree at a time or less, we can come up with some ideas here. Ultimately, a molecule likes to be least crowded. This conformation where I have the 2 carbons, I'd call that carbon 2 and carbon 3, I kind of hold it into a same parallel plane, and this first carbon coming up and the 4th carbon coming down of this imaginary plane right here. What this is doing is easing crowding. If this is my imaginary plane between carbon 2 and 3, carbon 1 is above the plane, carbon 4 is below the plane, very much easing a crowding between those methyl groups off of those center 2 carbons. But now imagine, if you can, grabbing this with your molecular model and just twisting it up. Twist it up. So now in carbon 2 and 3, here's my imaginary plane, but what's happened to the crowding by that rotation? Notice this methyl group and this methyl group are now so close together, they don't like that. It's just, the like charges of hydrogen start to repel each other, and this is not a very stable conformation. And if you keep twisting and start bringing the hydrogens closer and closer together, this is a very crowded structure, very unstable. Molecules are going to prefer to arrange themselves so they can ease crowding of those alkyl groups or the ends of those carbon chains. So what we're talking about with a conformation, the entire structure in a three-dimensional way, how can they arrange themselves with bond angles to alleviate crowding? Here's a molecule called cyclopentane. Now remember, we just did a straight chain and talked about one up and one down with the butane. But now if you actually build this, you're going to see something in terms of connecting, just kind of build yourself a 5-carbon chain and then take this carbon, you're going to have to twist them together and try to rotate those bonds together to get these guys to hook. And the resulting compound ends up in a cyclic structure where 4 of those carbons, 4 of the 5, lie in the same plane, and the 5th one's going to sit up high. That eases the crowding. That conformation is known as the envelope conformation, a five-membered ring where four of them lie in the same plane. Literally, you could grab this particular carbon, and if you force it to go down into the same plane, you can't help but have another one pop up. If I grab this one and push it down into the same plane, another one's going to pop up. Four of the carbons will always lie in the same plane, with the fifth one poking up high out of the plane. In cyclohexane, again, imagine, how can I take 6 carbons in a row in a straight chain and find a way to connect, literally grab the last carbon and then this last carbon, those two terminal carbons, try to arrange bond angles so where they kind of meet and form a cyclic structure. Just as the 5-membered ring had 4 carbons that lie in the same plane, the 6-membered ring does as well. The 6-membered ring has 4 carbons that lie in a plane. One of them will be poking up, the other will be poking down in what's called a chair conformation. This is the most stable arrangement. Now, I can, with a whole lot of twisting, convince both of them to come up. If this represents kind of my 4-carbon plane, taking this molecule here, this end carbon, and trying to twist it up into the same plane as the other guy. I mean, it will work. It's just not very stable because all of a sudden now the molecule becomes extremely crowded. What it likes to do is to create this chair conformation. Now use your imagination. Why is it called a chair conformation? Well, a chair, if I'm sitting here, has a back where I can rest and a set for my legs where it can rest. So imagine myself laying in this chair conformation of a cyclohexane ring. This is not a chair conformation because I end up having both of those carbons up into the same plane. That's not the most stable arrangement. Having one up and one down from the 4-membered plane is indeed the chair conformation. What we try to do, and this to me is a skill, trying to draw the chair conformation using just the structural models. So I kind of draw best I can a 6-membered ring representing a chair conformation. This has got to come down a little bit more. Hey, that's not too bad. I'm trying to draw, if you have your book nearby, page 335, the chair conformation in a line drawing where each carbon is now being represented kind of in its 3-dimensional shape. You know, the more you take organic chemistry, the faster you get at these. I've just never been a very good drawer. As those who know me know, I struggle trying to draw anything 3-dimension. So best I can, I go, okay, I'm going to draw the first guy, and then I come back and try to draw up the second guy, and I get a little better with practice. Perhaps you will as well. Alrighty. But we get the idea, the chair conformation coming from a person literally sitting in a chair, head up, feet down. Let's discuss then in cyclohexane the chair conformation. Again, we just were practicing drawing that, the chair conformation. Here I am trying to draw that structure. And talk about the positions of those carbons. And remember, cyclohexane, C6H12. It's just 2N giving me the number of hydrogens. Okay, so if N represents 6 carbons, the hydrogens would be twice as large because I've removed the 2 hydrogens at the terminal carbon to hook them together in a cyclic structure. Some vocabulary. When we look at those 4 carbons that are in the same plane, 1 carbon pointing up, 1 carbon pointing down. Drawing them again kind of in a structural line format. These are the same representations of a cyclohexane. 6 of the 12 carbons lie in the same equator as those 4 carbons that lie in the same plane, and 6 of those bonds lie in the same axes as those carbons that are in the same plane. Now let's say that again. The equatorial position on a chair conformation, kind of what we're looking at here, those are the hydrogens that extend from the ring roughly perpendicular to the imaginary axes of the ring. If this is the axis of the ring, how it goes through, up and down, through the middle of the cycle, the equatorial lie in the equator. So that word to me means equator. If I find the parallel line between those 4 carbons that lie in the same plane, and I have hydrogens that are coming off in the same direction, kind of hooked in the same parallel line of the equator, those are going to be known as the equatorial. They literally, if you build this molecule, all of these hydrogens lie in a nice circle as an equator goes around the Earth, imaginary. However, the axial bonds are definitely up position or down position. The axis that goes through the center shows that if it's straight up or straight down, we have indeed the axial position. If they are in the same circle as those 4 bonds of those 4 carbons, and again that would be carbon 1, 2, 3, and 4 in the center of that structure, carbon 1, 2, 3, and 4. If they are indeed in that same circle, we call those equatorial. If they indeed go straight up, straight down, we call those the axial positions. In that most stable conformation, and we start placing substituent groups onto the cyclohexane structure, we will label those as equatorial, lying in the same imaginary equator, same parallel plane as the cyclic structure, or we could label them as axial, straight up, or perhaps you could have written that straight down, could be the methyl group. So substituent groups can either be equatorial, and again, if I just see it coming off in the same plane, equatorial positions. All of those would represent ways that molecules can just have a little branch coming off, lying in the same plane. You'd have kind of the same bond angle, the same feel for what's coming out here. Here would be the next. Those are all ways to show equatorial. And if I wanted to show axial positions, I would have one going straight up, one coming straight down. So straight up or straight down, axial. Lying in the same plane, the equatorial positions. When I look at example 11.6 of a chair conformation, it says we have a following cyclohexane structure showing a methyl group and 1 hydrogen. Let me try to draw that best I can. I'm going to try to draw my equatorial chair position. Again, I get better, but I'm always a little rusty. I see a CH3. I got to make that neater. I have a CH3 coming straight up, and I have a hydrogen kind of poking at the side like this. Label methyl cyclohexane, methyl cyclohexane. Hear that, how we named it? Oops, I spelled that wrong. Cyclohexane. Carbon number 1, and it's the only substituent group because hydrogens are coming off of everything. Hydrogen is not an alkyl functional group, so it's just a CH3, so no number necessary. But I also can note that it's in the axial position. The methyl group is axial, where the hydrogen group is equatorial. And I'm getting that just by the direction. The straight up line gives me the axial position, coming off at an angle that's matching the equator, the equatorial position. If we're asked to draw a structure, a little better. That's a cyclohexane chair conformation. You're probably laughing at me. And I number them just for order of convention. Let's call this carbon 1, 2, 3. This is a straight line. Carbon 4, 5, 6. What might the following structure look like if I put a methyl group that's equatorial on carbon 1, carbon 2, and carbon 4? Now, equatorial is saying it must lie in the same plane, not straight up or down, but in the same plane. Well, here's carbon 1. What would that look like if I place a methyl group off of carbon 1 lying in the same plane? We're going to simply extend and make a CH3. Not straight down, but extend the line. Carbon 2 is going to extend in this direction, CH3. Carbon 4 is going to extend, and notice it's going to go in this direction, extend and create a CH3. Build these and show yourself if it indeed lies in the same circular equator, you'll see it coming off at an angle. Now, it didn't ask us, but okay, so don't necessarily draw this as an answer, but axial, straight up, axial, straight down, axial, straight down. But when we're asked to draw those equatorial, put those at an angle to represent they're in the same equator as the actual 4-carbon member chain in that iso chair. Another type of configuration of a cyclic structure is called cis and trans, specifically to the alkyl functional groups. What are the alkyl branches coming off? So let me just repeat myself. Cis and trans isomers, cis and trans, are going to tell me the arrangement of an alkyl functional group, an alkyl chain, some kind of something hanging off of the cyclic structure. When we talked about the chair conformation, that's of the ring itself. Cis and trans are telling me what type of groups are coming off of the chain and how are they arranging themselves in a three-dimensional space. So if I already make the assumption I have a 6-sided carbon ring called a cyclohexane, I can have those functional groups hanging off on the same side of the ring called cis, or I can have those functional groups coming off on the opposite side of the chain known as trans. Let's take a peek. A 6-sided carbon ring, and notice these are all axial, aren't they? Every one of them is axial, up, down, up, down. I have cis 1, 2 dimethylcyclopentane. Cis is telling me they're on the same side of the cyclohexane, the cyclic structure there. Trans, one is pointing down and one is pointing up, opposite ends. Now if you build this, you'll see the chair conformation. Here's one of the methyls, here's the opposite. So if this is the imaginary plane going through our molecule and one is up of the plane and the other is down on the plane, it's trans. If we twist it around and both end up to be on the same side, we call that cis. The same side actually is more unstable, you guessed it, because these are very crowded. I can ease the crowding by putting the trans conformation in instead of the cis. If we view that same structure from above, notice here I'm getting dark lines to represent that they are above the cyclic structure. I can see both of them if I'm looking up above. Cis. However, if I twist it and look from up above, this one is kind of underneath. Underneath would kind of get represented by this dashed line. So if this is the plane and I'm looking for it, and this looks like 1, 2, 3, 4, 5, and I have one of those up above the plane, you'll see that as a kind of a wedge here, but it's colored in solid. And if it's lying below the plane, kind of out of sight, you'll see that represented with the dashed line. If I see both are above the plane, solid line. You know, if I took this molecule and just turned it upside down, I would have a structure, still it'd be cis, but I'd have them both underneath the plane, so that could be represented with dashed lines for both. If both are dashed lines, cis. If you have one dashed and one solid wedge, you know that they're in opposite sides of the plane of the cyclic structure. We know that to be a trans. To determine cis-trans isomers in kind of a di-substituted cyclohexane, try to view it in a planar hexagon. So let's take a peek. And again, if you have your models, it's worth building. Here we have a cyclic structure with 6 carbons. I notice one is below the plane and the other methyl group is above the plane. Carbon 1, 2, 3, and 4, always on the opposite ends here. So we have carbon 1 and 4 having a methyl group. Opposite sides of the plane, so you'll hear that trans dash, carbon 1, 4 dash, dimethyl cyclohexane. 2 methyl groups that are in opposite sides of the plane. This is a view of me holding it on my hand and looking down, looking right straight through the molecule. Notice they're on opposite sides. On carbon 1 and on carbon 4, one of the methyl groups is above the plane. One of the methyl groups is below the plane. That's why we see the dashed line kind of out of view because it's underneath the cyclic structure. The solid wedge here is telling us that it is above the plane. One solid wedge, one dashed wedge, and we now know it's trans. Here we have a structure where the 2 carbons lie in the same plane underneath the cyclic structure, thus the term cis. At carbon 1, 2, 3, 4, we have 2 methyl groups, but because both are lying underneath, we call it cis. Cis dash 1, 4 dash dimethyl cyclohexane. And to show the cis, we show either both dashed lines, or it could also be represented with 2 solid wedges, just so that we know they're the same. Both could be on top or both could be on bottom, but they need to be the same. So 2 solids wedge would show cis, or 2 dashed wedges show that they're being hidden from view, but a cis conformation. Because cis and trans isomers truly are different in orientation, they're called stereoisomers. Stereoisomers are just one example of many to be studied of stereoconformations. Chapter 15, kind of seeding a next lesson, and enantiomers are those types of things we study and when we get into things called chirality. Stereo is like a 3-dimensional isomer, truly just different by the way they arrange their atoms in space. Arrangement of atoms truly does determine physical properties and the way that these molecules behave when placed into solvents, or heck, even in biochemistry, into our bodies when they try to recognize their substrates. (11.7). Let's try some of these. I have a structure that says, for which of the following cycloalkanes show cis-trans isomerism? For each that does, draw both isomers. All right, let's make sense. I'm going to write a word. It says methyl cyclopentane. Methyl cyclopentane. Could this possibly show cis-trans isomerism? Cyclopentane says I'm going to have a 5-membered ring, and I'm going to have a methyl group coming off of it. Or just simply a straight line. I didn't need to draw that. Probably should get in the habit of not mixing up our formulas. I'll just draw a straight line. There it is. Methyl cyclopentane. Well, this indeed does not show cis-trans, because at least I have to have 2 substituent groups coming off to have a cis and a trans possibility. So this does not exhibit cis-trans isomerism. Letter B. 1,1-dimethyl cyclopentane. Dimethyl cyclopentane, giving you a moment to write that. Let's draw that structure, cyclopentane. Well, if I have cyclopentane, I have 1, 2, 3, 4, 5. 5 carbons. At carbon number 1, I have 2 methyl groups coming off. the two methyl groups, and it's saying it possibly cannot show cis and trans because they're coming off the same carbon. To show 1, 2 methyl groups coming off of any of those carbons would have done, but I'll call that carbon 1. 1,1 dimethyl. Now notice, because we have two substituent groups, we do require numbers. I have to let you know where both of them are, and they happen to be on the same carbon. But in order for cis and trans to occur, they have to be on different carbons. I mean, there's only so many bonding spots here. There's no way I could manipulate these. Because both methyl groups are bonded to that same carbon, they have to be trans to each other. There just isn't any other conformation. There's only one ring above, and the other has to be below. So no, this cannot show cis-trans isomerism. How about 1,3 dimethyl cyclobutane? 1,3 dimethyl cyclobutane. Cyclobutane, four-membered ring. But now if I think about a better way, just kind of geometrically, and if you had kind of built this, you would notice that you end up with more of a structure that's at an angle, kind of like this. It doesn't end up more as a box. I can kind of twist that and see more of it as a triangle. 1,3, so let's call this carbon. I'll call this carbon 1, carbon 2, carbon 3, carbon 4. And now we have two methyl groups. But now see how they're on opposite ends of a cyclic structure? Could this possibly show cis-trans isomerism? And I say absolutely. Because if I look at this structure, I can place the methyl group up high on both sides and create a cis. I could have put both below, doesn't matter, but they have to be on the same side. Or, kind of drawing my structure again, I could have placed one on top of the equator and then one below the equator, and I could have come up with trans. So see the criteria here? We have a cyclic structure where on opposite ends of the ring, we can place one group up, one group down, or indeed on the same side to create isomerism. The other way to draw this, kind of thinking about the wedges that they'll ask us to kind of compare that. If they are cis, we're going to take a look at drawing them either with solid wedges or with, I'm going to try to draw, both need to be solid or both need to be dashed, but they just need to be the same to represent cis. And over here, trying to draw with this marker here. Again, one would have to be a dashed line, and the other then would come off as a solid wedge to indicate trans. Doesn't matter which side I put them on, because I could just literally flip the molecule. This would be a good place to stop and let you study through the conformations of cis-trans and trying to get your handle on drawing as many as you can, or even building them to show cis-trans isomerism, chair conformations, kind of easing the crowding and rotating bonds to get an idea of what stereoisomers are and what conformational isomers are. When you feel ready, start the lesson again. This time we'll be talking about physical properties of alkanes.